In this talk, I'm going to be looking at real resistors and their properties. A quick reminder in case you're not sure what I mean by surface mount and through hole. A surface mount resistor is mounted on the surface of the circuit board. This is a surface mount resistor here. It's soldered to a couple of pads on the surface, the top of this circuit board here. Through-hole resistor is something like this one here, which has leads which go through holes in the circuit board and are soldered and fixed on the other side, on the back of the circuit board here. Right, on to resistors and their parasitics and their equivalent network models. Surface mount resistors are made by taking a ceramic block. Ceramic is chosen because it's very cheap and it has very good high temperature properties. It doesn't tend to sort of expand with temperature as the resistor gets hotter, and it can cope with very high temperatures. And you put on top of that ceramic block a very thin conductive film. And if you make that film narrow enough, you can make very high value resistors. Place a metal termination cap on either end, which can be soldered to the pads on the circuit board, and put a protective paint and the numbers on the top, and you have a surface mount resistor. They tend to have very low parasitics. In other words, they tend to behave approximately like ideal resistors. You don't have to worry too much about any inductive or capacitive effects of surface mount resistors until you get to very high frequencies. Through-hole resistors, on the other hand, do have significant parasitics that we often have to worry about. They're made in a similar way. It's a ceramic carrier, in this case a small cylindrical bit of ceramic, with again a very thin conductive film placed around that ceramic cylinder. In order to increase the value of the resistance, you can then cut a helical groove through the conductive film, which effectively lengthens the conductive path that the current has to take through the resistor. And that increases the value of the resistor. Now, this introduces some parasitics. First of all, you may have noticed that what we've effectively done is we've got a coil of wire which is going around a central core in a coil. But that is exactly how you make an inductor. So you might expect these resistors to have a significant parasitic inductance, and indeed they do. There's also a very narrow gap between these parts of the film here, and if you have a voltage across the resistor as a whole, the voltage on both sides of that narrow gap is going to be slightly different. Well, if you have two conductors at slightly different voltages, with a very narrow gap in between them, that's a capacitor. And we have a small parasitic capacitance with these resistors as well. Through-hole resistors like this can deal with fairly small powers quite easily. If you want to deal with a much higher power, then you would typically move to a wire-wound resistor. Wire-wound resistors look like this. Same idea, a ceramic core, but this time instead of having a film which you cut a helical groove in, you actually have some resistive wire which you loop around that core, which again is exactly how you make inductors. So you tend to have some parasitic inductance with these resistors as well. There are construction techniques that you can use to minimize that inductance. One simple way is to have the first half of the wire-wound resistor wound in one direction, say clockwise, and the other half of the wire-wound resistor wound the other way, anti-clockwise. And if you do that, the magnetic fields caused by the two halves of the winding tend to cancel each other out. And with no net magnetic field, you don't get any induced EMF and therefore no inductance. It's not perfect, and you will get a small amount of inductance associated with any of this type of resistor. This particular resistor is then put in an aluminium body with some holes in its outer case there, which will enable it to be screwed or bolted into a heatsink to take a lot of the energy that's being dissipated by this resistor away from the resistor itself. Now, this is a model which is commonly used to predict the behaviour of resistors. It's not entirely accurate because the capacitance does not occur in a single external parasitic component in parallel with the rest of the resistor. It's more of a distributed capacitance throughout the whole of the resistance itself. So there is a slight inaccuracy in using this simplified model, but the fact that this model only requires 3 components makes it much easier to work with than any more complicated model of a resistor. Typical values of the capacitance for a small through-hole resistor would be around about 50 femtofarads, and typical values of the inductance there would be around 10 nanohenries. And we can use those figures to determine what range of resistors we can use and not have to worry about the fact that these parasitic components exist as part of the real resistor. Remember that the resistor has this equivalent model with a parasitic capacitance there of around 50 femtofarads and a inductance here of around 10 nanohenries for a typical small through-hole resistor. Now, if we want to know what values of resistor we can use and not have to worry about the effect of these 2 components, then we have to define what frequency range we're interested in. At very, very low frequencies, the capacitor effectively has an infinite impedance, and the inductance effectively has 0 impedance, and we don't need to worry about either of them. As the frequency goes up, the impedance of the capacitor will come down, and the impedance of the inductor will go up, and that will start to increase the impedance of the overall component. For very low values of resistor, it's the inductor that we have to worry about. For very high values of resistance, it's the capacitor we have to worry about. We can put some numbers into this by assuming a frequency range. Let's say we're interested in the frequencies up to 1 megahertz for these through-hole components. And we want to know what values of resistor we can use and not have to worry about these parasitics. And by not have to worry, I can define that as being the total impedance of the component is less than 0.5% different from the ideal value of the resistance. For a resistor, we may typically pick a 1% resistance, so having another 0.5% inaccuracy due to these parasitics isn't going to affect the circuit very much. So, we can now start to work out what values of resistors we can use. First of all, let's consider very low values of resistors. Now, it's not quite as straightforward as you might think. We can't just, for example, work out the impedance of this inductor at 1 megahertz. As you could see, that would be about 63 milliohms. And then say, well, if that's 0.5%, then we just multiply that by 200, and that's the value of the resistor. It's not quite as simple as that, because this impedance of the inductor is a complex impedance. And for an inductor, that means an imaginary impedance. If we were to draw out the situation on an argon diagram, we have a resistor of value R. The impedance would be along the real axis. And we have an inductance of value, in this case, 63 milliohms. And that would be a complex inductance. It would actually be J63 milli, and it would be straight up in that direction on an argon diagram. Real, imaginary. And the total impedance of the component, and I'm not worrying about the capacitor for now because the resistance is so small, would be that hypotenuse there, or at least that's the magnitude of the total impedance of the component. And if that is only 0.5% bigger than the specified value of the resistor, then the length of this hypotenuse must be 1.005 R. So, all we have to do is apply Pythagoras and solve this right-angled triangle. And that means that R squared plus 63 milli squared is equal to 1.005 r squared. Or in other words, 1.005 squared minus 1 times r squared is 63 milli squared, or the square root of 1.005 squared minus 1 times r is 63 milli. R is 63 milli divided by that. Plug those numbers into a calculator and you get about 0.63. That's 0.63 ohms. If we use a resistor smaller than 0.63 ohms at 1 megahertz, then we would have to worry about the effect of this series inductance here. What about the effect of this capacitor here? Well, that's going to start causing a problem for very high values of resistor, when a high value of impedance of this capacitor is not going to be negligible compared to this high value of this resistor here. Since these two components are in parallel, we can't do quite as simple a technique as this, just adding up the complex impedances on an argon diagram. But what we can do is play a little trick and add up the inverses of the component values. For two components in parallel, we have that 1 over z total is 1 over z1 plus 1 over z2. And z1 and z2 are complex numbers, so 1 over z1 and 1 over z2 are going to be complex numbers as well. So let's do an argon diagram, but we'll plot 1 over the impedances rather than the impedances themselves. That would give us this. Well, 1 over the impedance of our resistor would just be a real number with a value of 1 over r. 1 over the total impedance has got to be within 0.5% of this. So we'll draw that, say, up to around about here. And that's going to be 1.005 over r. 0.5% above 1 over r. The difference there, that is the contribution of 1 over Z2, 1 over the impedance of this capacitor. And from the table here, we can see that the impedance of the capacitor is 3 mega ohms. Actually, it would be minus J times 3 mega ohms. So if Z2 is minus J times 3 mega ohms, 1 over Z2 must be 1 over minus J times 3 mega ohms, which is just J over 3 mega ohms. So this will be J over 3 mega ohms. And once again, we can just apply Pythagoras. 1.005 squared over r squared must be 1 over r squared plus 1 over 3 mega ohms squared. Multiply everything up by r. 1.005 squared minus 1 equals r squared over 3 mega ohm squared. So r squared would be 3 mega ohm squared times 1.005 squared minus 1, or r is just that. Plug some numbers into a calculator and we get 300k. So 300k is the biggest resistor we can use without having to worry about the effects of this capacitor at 1 megahertz. You can get the values of the parasitic inductance and the capacitance from a good resistor datasheet. Next time, we'll have a look at capacitors.